So we have a uniform rod of length L, and it's rotating in the bubble at constant angular velocity omega, about a fixed point P. So we need to find the tension in the rod. Okay, and some things that you might need to worry about. First, is the tension in the rod uniform? That is it the same at all points along the rod? Why is there any tension in the rod? Well, why does there need to be any tension force in the rod? Yeah?
Because if it's rotating, then it
Yeah.
experiences centrifugal force, but assuming that the rod doesn't like stretch or compress, there has to be an opposing force.
Well, okay, so if it's left to itself, what will it do according to Newton? Move in a straight line at constant velocity. Is it moving in a straight line at no. Okay? No. All right. Therefore, we know there must be forces on the masses because they're not moving in straight lines at constant velocity. Ergo, must be forces. Okay? Is the force then uniform throughout the rod? Does it have to be the same everywhere along the rod? Think about like extreme cases like the ends. What must be true about the force on the right end?
It's going to have to pull out.
The right end, the outer end is moving faster. So divide and conquer, I get to chop this up however I like. Suppose that I chop it up and I consider just that little bit. Okay, so I do an isolation diagram. I have that little bit only. Are there any forces on that little bit at the end of the rod? Which way? Has to be towards the center. Okay, so there's a force. Who supplies that force? Yeah, the atoms that are right next to that, I make my virtual cleave, the bonds that are in the rod there are supplying that force. Okay? So this little bit has, let's say, a mass dm, and so whatever the acceleration has towards the center multiplied by dm, that must be the tension in the rod there. So is that going to be the same all the way along? Why not? There's different acceleration. Imagine I now consider this little more arbitrary bit inside. What are the forces on it? Aha! So there's going to be some tension down this way. There's going to be some tension that way. And there's still acceleration towards the center. So let's say that I use a coordinate r to go up to this little slice. So the thickness of the slice could be dr. So this is going to be the tension at r. This will be the tension at r plus dr. Agreed? Okay. So I have my isolation diagram, except that I'm missing something. What do I have to put on it? The acceleration, direction. I'm picking. Which way would you prefer? Towards the center. That's the way it's actually accelerating. So I'm going to put A that way. And my F equals ma equation will be sum of the forces in that direction. So that's T at r minus T at r plus dr. Must be equal to dm, the little bit of mass in that slice, times A. Are we good so far? Now, we derived last time an expression for the acceleration for something that goes around in a circle at constant angular velocity. What was it? This should be omega squared r. Okay. How about dm? Can I express dm in terms of dr? It's a uniform rod.
So it's dr.
Can we use, yeah, I heard it. Proportionality, can I say dm over all the mass is equal to dr over all the length, which I guess is L. Does that work? If it's uniform? Yeah, each part has the same density and so the same amount of mass. So I could express dm as equal to m over L times dr. Okay, so what do we got? We're almost done, believe it or not. We have, it's going to look more familiar if I multiply both sides by -1. So I can put this first, tr plus dr minus t at r is equal to, and now I need a minus m over L dr times omega squared r. Okay, what if I were to do this? What do you call the thing on the left, at least in the limit as dr goes to 0? That is the derivative of the tension with respect to r. So this is dt dr is equal to minus m over L omega squared r. Can we solve that? How? Okay, so this says I'm thinking of a tension, but I know the derivative, and the derivative is proportional to r. So I integrate, so I can say integral of dt dr with respect to r must be equal to the integral of minus m over L omega squared r with respect to r. And I'm going to worry about limits at the end. So on the left, I get the antiderivative of t is just the tension t. And on the right, what do I get? Minus m over L omega squared r squared over 2 plus some crummy constant.
Can't we just evaluate it from 0 to m?
Hang on one sec. Okay, so now I know the answer up to a constant, and are you bothered by the negative sign?
No.
Can the tension in the rod be negative? Where is the tension equal to a simple value? Yeah, which part of the rod doesn't have to pull any other mass to go in a circle? P has to pull all the mass to go in a circle. So close! So on the farthest end, it has nobody left to the right to pull in to go in a circle. So the tension at the far end is 0. The tension at r equals L is 0. So T of r must be equal to, how am I going to plug in C so the tension goes to 0 at L? I'm pulling out a bunch of common factors, m omega squared over 2L times, oops, that's supposed to be L squared minus r squared. So I wrote my constant C in a way that factored out a whole bunch of common stuff so that it's clear when r is equal to L the tension goes to 0. Okay, so we're out of time. I just want to emphasize on this problem, we had to carve it up into little bits because the acceleration of each little bit was different. The tension was different. But if we carve it up into infinitesimal bits, then we can apply our divide and conquer approach, F equals ma. See you on Monday.